Hello to those that are just joining us. I'm still buzzed off our last session. I'm a very, very competitive person. So I don't know if you'll notice there's a little sheet next to you that has a barcode and explains our cognition app. I'm trying to get as many people from this room to get onto the app. So please do join me in doing that, and make sure you do scan and get onto the app and explore all of the audio and content that we have available. Next up, we have our next session where we'll be exploring molecules and quantum mechanics and loads of things that begin with an M. And I'm really excited. So I'm going to hand it over to Alice, who's moderating, and introduce our awesome speakers. So can we give them a round of applause, please? Awesome.
So hi everybody, both those of you that are here and those online. So yes, I'm Alice, and I'm a postdoctoral research scientist working in machine learning and computational physics. And in today's session, we will be looking at how machine learning and physics can be used together, and the improvements that can then come in modeling materials and molecules. And we have here today Ed and Gabor. So why don't we just begin by you introducing yourselves and telling us what it is that you do?
Go ahead.
Yeah, sure. Thanks a lot. So yeah, I'm Ed Grant. I'm Chief Science Officer at a company called Rahko, and we focus on drug discovery using a combination of machine learning, quantum computing, and quantum computational chemistry.
I'm Gabor Csanyi, and I'm a professor of molecular modeling at the University of Cambridge, and I do molecular modeling and machine learning too.
Great. So to give some motivation of why we're here, do you just want to tell us why we should care about modeling materials and molecules?
Yeah, absolutely. So I guess materials and molecules are some of the most complicated systems that we kind of have in the universe. And I think traditionally to discover new molecules and materials, people have relied on scientific intuition and really experiments in a lab or a facility. And this is fine, except for that it's extremely slow. So if we're able to actually use modeling principles and actually do this computationally, what it means is that we can use that intuition to actually screen through a far more vast region of chemical or material space to kind of find the materials that we're looking for. Do you want to add something, Gabor?
Yeah, so materials are all around us. We are made of materials. All of our technology is made of materials. And as well as making them better through computational modeling, we can also understand them. So by looking at how materials and molecules operate at a variety of length scales, the length scales of our cells, but also on the microscopic length scales, on the scale of individual molecules and atoms, and even lower, we can actually understand how these how materials and molecules work, what makes them have the properties that they have.
And what are some of the applications? Like, how is this actually used in real life or in industries?
So this sort of understanding, for example, one of my favorite, most recent examples is about making steels. So if a steel is a very strong, we can make it a very hard material, a very strong material, but sometimes it breaks, and we want to understand why that happens, how that happens. It turns out that hydrogen, the smallest atom that there is, when it gets into steel, it makes it brittle, and that's a 150-year-old observation. We don't still really understand how and why that works.
And so what about machine learning? How does this fit into everything to do with modeling materials?
Yeah, sure. So materials intrinsically have quantum properties, and sometimes these quantum properties can actually dominate. And modeling these using classical computers and classical machine learning can actually be very difficult. So there are a variety of kind of methods, and they all make approximations to these quantum mechanics. So we have some kind of very efficient, fast methods that actually ignore a lot of the quantum mechanics. And as you progressively kind of increase the kind of power of these methods, you include more of the quantum mechanics, you get more accurate results. But actually, it becomes very computationally expensive to do it, to the extent where if you really want to actually model these systems at a full quantum level, it can actually become completely intractable or impossible for large systems. So what machine learning is very good at is actually learning from these simulations, or the output of these kind of calculations and simulations, and actually then being able to do very, very fast inference. So the idea is that you can get these a small number of very slow, expensive calculations or simulations using as much of the quantum mechanics as you can afford to use. But you can then use that to train a machine learning model, and the machine learning model will have similar kind of accuracy, but actually be much, much faster. And I think that's really the kind of promise of combining machine learning with these computational simulation methods. I'm sure Gabor has a lot more to add.
So this speed issue is exponential. It's very difficult to model a material on its large length scale using its small constituents. So and that happens at all length scales. So if I have a jet engine and I want to understand how the air and the fuel and the gases that are produced flow through it, that's a massive computational model that I need to run, and that's just talking about fluids. We're not yet talking about the molecules that make up those fluids. And then you can come down onto lower length scales. If I have a piece of protein that has hundreds of thousands of atoms perhaps, and how that protein aggregates with other proteins, how it operates, it's very difficult to model that using these constituent pieces. And machine learning is now helping us, and that's the new thing about it, is helping us to link these length scales. So I can use it to predict how big flows happen around the jet engine, around a cup of coffee. And I can also use it to understand how a protein operates, how a molecule operates, how a molecule works, given all the electrons running around in it.
Okay, so quantum mechanics, we can't currently do things which are very long timescales and very big systems. Is that what you're saying?
Yeah, and the scalings are very poor here. So one of the quantum mechanical methods that we use here, called density functional theory, we can run it for a few hundred atoms for a few hundred time steps if I want to simulate the motion of a molecule. But the costs scale cubically with the system size. And that's for typical implementations. And that means that it's prohibitively expensive to run it for very, very large systems. And that's where the machine learning methods help.
Right. Okay. So we should be able to have these cheaper simulations for much longer at the end of it. And where are we currently then with machine learning for quantum mechanics? What can we currently do with it?
I'll take that. I'll start on that. Really, this is about a 10-year-old field. And it's safe to say that there is a revolution underway in molecular modeling. With these new techniques, we can do things that we've never been able to do before. We can compute with quantum mechanical accuracy the properties of molecules on a length scale where we couldn't do before. And the same goes for materials. So recently we published a piece of work with colleagues from Oxford where we simulated 100,000 atoms under severe compression, and new phenomena were identified because we were able to do it with quantum mechanical accuracy, whereas before the largest simulation one could do was about 200 atoms on that scale. And this still is a very small length scale compared to our everyday length scales, but it's a big enough step that we can find out new phenomena when we do that.
I think two things that have been really important is just access to kind of larger data sets. That's important kind of in all areas of machine learning, and also access to the hardware that kind of opens up new possibilities, things like using GPUs and TPUs in this context as well. I think that's been, that's been extremely important for the field. I think something that's really kind of really just taking off at the moment is understanding the kind of priors that you want to build into your models and your feature space to actually extract the most juice from the data. So I guess like in computer vision, convolutional neural networks were one of these kind of priors that people infused into these deep learning architectures that allowed them to generalize much better and learn better from much less data. And in this domain, because the data can be extremely expensive to generate. So what's really important is being able to actually really make the best use of that data that you have. And this is really extremely, a lot of the best work I think has been done in Gabor's lab on the kind of making sure that the features that we're using are very descriptive and expressive. But also you want to have models that actually are infused with these kind of priors from physics and quantum mechanics. And I think what we're seeing at the moment is really the kind of these two things coming together.
So there is a story here, which is that people tried applying very standard off-the-shelf machine learning methods, and they kind of did something, but the efficacy of these methods became orders of magnitude larger when we learned how to put in symmetries, so physical symmetries. If I have a molecule and it's oriented this way, actually its properties are not changed if I rotate that molecule. But that's not true for an image, right? If I want to recognize letters, then I take the letter P, and if I rotate it by 180 degrees, it's a different letter. So, but in physics, in chemistry, in this quantum mechanical world, there is a lot of symmetry. Rotation is an example. And when we learn to put that symmetry into the models exactly, then suddenly everything started to work much better.
Okay, so that's something that's maybe different about other areas of machine learning. You have to start putting physics into the models themselves.
And that's in every case, and there are many advances over the past 10 years where people have learned to put yet another piece of physics into it. Rotational symmetry is one, but limiting cases. If I take two molecules or two atoms, maybe I can understand, maybe I know what happens when I separate them very far. And that's a limit, which if I can build that into the model, then the model becomes better.
Okay.
I think, also something that machine learning is historically not very good at is being able to predict things that are outside of the distribution of the data that it's trained on. And I think also that's why the kind of descriptions of these kind of systems of molecules and materials that we use is extremely important, because, for instance, if you're using just say a very basic geometric description, if you then try and make a prediction about a system that's double the size, actually it's going to be out of the distribution in terms of what the model's seen, and it's going to fail. But if you can really bring this back to a more fundamental description that's based on the physics and based on the quantum mechanics, then it's going to be much better at extrapolating. And I think that this is going to be this is kind of a really core focus of the field at the moment, to try and get these really kind of rich fundamental descriptors that'll allow us to do this kind of generalization and extrapolation.
That's a really, really important point. I'd like to pick up on that. So if you think about a more traditional machine learning task, for example, recognizing faces, suppose that the job is that faces come maybe at the UK border, and you want to create an algorithm that recognizes them, matches them to names. Then we can talk about the efficiency or the accuracy of that. And if you have a 90% accurate algorithm or 99% accurate algorithm, those are very, very useful. And you can compare that to the accuracy that say a human official serving in that role would have. And a 99.9% algorithm is very, very accurate and will reduce costs and so on. But if you think about a quantum mechanical simulation of a material, if I tell you that I have a model that is 99% accurate, what does that mean? Does that mean that 99% of the time is going to give me the right answer and 1% of the time some completely crazy answer? And if I try to simulate with that, the molecule may explode after 99 steps. That means that my simulation actually has to be stopped and it's useless. So the requirements on what we want from these machine learning models is actually subtly, but very importantly, different. And this sort of generalization property and extrapolation property is much, much more important than with traditional ML applications.
So in terms of the current state, so we're already at the point where you can get new physical phenomena, right? And we've already got to that point. But what about the limitations that still exist? What can't we do, and why are we not there yet?
I think one of the things that will not happen is machine learning is not going to replace experiments, and it's not going to replace doing explicit quantum mechanics, because the data that we train our machine learning models from are the physical theories. Something that is very, very exciting and is just starting, and I think it will grow in the next 10 years, is not only predicting properties of molecules and materials, but using the machine learning algorithms to generate new kinds of ideas for new molecules. You're working on something like that.
Exactly. So historically in the pharmaceutical industry, when you would trying to find a kind of hit candidate for a particular protein that's correlated with the disease, one way that people might start is actually with a very, very large data set of molecules that might have some drug-like properties, and they'll try and screen through them to make sure that they have the correct toxicity profile, that they'll be absorbed correctly, whether or not they'll cross the blood-brain barrier, and also that they'll bind to the site that they're meant to, and also be selective, so not bind to the site that they're not meant to. But even if you start with a very, very large data set, actually by the time you've filtered this down, to actually the subset with all the properties that you want, you might end up with actually nothing, or an extremely small set it's not quite right. So what generative modeling promises to do is to actually you start off with a set of properties, and then you generate the data set. And then, so you say, yeah, I want it to treat this disease. I want it to not bind to this site. I want it to, cross the blood-brain barrier. So you set all these parameters, and you say, now generate me a distribution of molecules that has these properties. And that's fantastic, because what you can then do is actually generate also a very, very large data set, but you've already started in a very good region of chemical space. And then at this point, you can use these more expensive fine-grained filters to actually whittle that down and end up with something, a far richer set of candidate molecules that you can take forward. So yeah, I think we're just starting on the cusp of being able to really do this in a meaningful way. But I think, over the next 10 years, this is probably going to be one of the most important areas of this field.
And certainly new methods new ideas and new understanding is needed to carry out this effectively. A lot of times when people have tried this up to now, they would generate a proposal for a new molecule, but it doesn't come to you as an idea of where the atoms are. It's in some sort of latent representation. And then you still have to actually generate a molecule that matches with that latent representation. And most of the time there isn't a molecule. So that sort of hit rate, to borrow that phrase from the pharmaceutical industry, is still very, very low. And new mathematics, new ideas on how to represent molecules so that this generative modeling can be done effectively is still needed.
Definitely, yeah.
But there are other limitations now. So we maybe don't have the speed that we need, or extrapolation and other things like that currently within the field. There's other limitations.
Well, I mean, it's my own work focuses on taking quantum mechanics to the next length scale, which is the length scale of atoms and molecular dynamics. But in other fields, at other length scales, we don't really know yet what the accuracy cost trade-offs are. So that's still to come. In the lower length scale, so the electronic structure, what does a quantum mechanical wave function of an electron look like? One can use machine learning type tools to try and uncover that, but how useful these techniques will turn out to be, we don't really know yet, and whether they will actually be useful enough to lead to new understanding and new science, I think that's still unknown. And the same thing at higher length scales. So thinking about how the atoms and the individual molecules combine to create larger structures, and then we want to create a machine learning model that predicts how those larger structures work and how they operate. These investigations are really just starting, and we don't yet know whether they will be worth it in the end, beating the existing ways of understanding those systems.
I think also one kind of unsolved issue is understanding, just so you have a fixed computational budget for collecting your data set that you'd like to use to train your model for a particular task, and exactly how to use that budget. So as I was mentioning before, there's these sort of different levels of theory that progressively make, as you go down, they make more crude approximations to the quantum mechanics or completely ignore them. So they're much less accurate, but they're much cheaper. So it's easy to generate, just say, sort of, thousands of data points at this level at a, very low cost. Once you start going up this chain, you want very accurate simulations. It ends up, these simulations on even on a cluster can start taking sort of weeks or even months. And so understanding with a fixed budget, in order to solve a particular problem, what kinds of data do we need to collect? And for some systems, actually, these crude approximations are kind of okay. But for other systems and other parts of systems, you really want to be looking at more of a much kind of like more quantum mechanical level. And there's a field called active learning that I think many of you will be aware of. And this is actually where you start to let your use actually the machine learning itself to decide what kind of data it actually needs in order to improve its overall accuracy. And I think rather than the human kind of just deciding, probably getting it a bit wrong, where and what, how and why to collect different parts of data, to actually ingrain that into the machine learning pipeline and really train your model to actually understand where and how and when it should be doing it needs data from these different levels of simulation.
There are some cases in which we see efficiency limitations that are starting to become apparent. Mm-hmm. So, for example, to calculate the force on an atom, to know where it's going to go in the next, if I simulate its motion in time, then it seems unlikely that we will be able to do that on a single CPU faster than 0.1 milliseconds. I just don't see, with the amount of information that has to be integrated into that calculation, how you could do that faster than that. So this places sort of intrinsic limitations on what this speed gain is going to be. And that 0.1 milliseconds is maybe 1 million or 1 billion times faster than what I would have to do if I were to do the original quantum mechanical calculation. And that's why we are so excited about this. But but it's becoming clear what the efficiency limitations are.
So there are these kind of fundamental limitations to what machine learning for quantum mechanics will ever do. Right.
I think so. I mean,
yeah.
how many multiplications do you need to do to get the force on the next atom? If you use the simplest non-machine learned empirical model, okay, it's 3, and you need more multiplications in order to get a better answer, and you'll never get down to 3 because there's only so much you can do by multiplying 3 numbers. So I think there are definitely these efficiency limits that we are starting to see emerging.
Okay, so there'll always be these faster models. Are there other fundamental limitations, or that's the main one you see?
Well, in many parts of machine learning, there is this notion of the curse of dimensionality, that when you're fitting functions in very large dimensional spaces, if those functions are very complicated, there are trade-offs that you can't get out of. You need much more data to fit a more complex function. And I don't think we are breaking, in some fundamental way, those limitations. We are just applying the existing approaches to fitting high-dimensional functions into this area.
And so one of the areas of interest in machine learning right now is to do with explainability and interpretability. Does this kind of like fit in with any of the work which is going on in this field? Or
Absolutely. Alice, maybe I could take this one. So I know this is your domain, your area of expertise as well, Alice. So, I mean, yeah, absolutely. So I think especially in drug design, there are humans in this loop. So your machine learning model will produce some molecules, but actually they need to be verified and validated by a medicinal chemist who needs to understand whether they can be synthesized, whether there's something a little bit funny about them. And also, once you've generated some good candidates, they typically go through then other periods of optimization where you're really optimizing for specific properties and trying to reduce that toxicity profile. And actually sometimes, so these medicinal chemists who have very, very good intuition about how to do this, but that can be really assisted by these algorithms as well. So you can actually use techniques that actually derive from computer vision to actually just say you have a representation of your molecule and you're predicting something like, just say, the cardiac toxicity. You might give a very high reading, but you really want to know why. And actually what you can do is you can use these kind of things like deconvolution from computer vision to actually map back into the input space. And what you'll get out is a kind of heat map of this molecule, of regions that contributed positively and negatively to this cardiac toxicity. And that's really, really useful, because if you can isolate a part of your molecule that said, okay, this is really the main cause of toxicity, then you can try and substitute that part of the molecule. So in that case, yeah, it can be extremely, extremely useful to have this type of explainability.
There's also a way in which these machine learning models help us to actually understand the quantum mechanical theories that we already know. So an example of that is that if you take a molecule, it has a certain energy in a certain configuration, and we can calculate that expensively using quantum mechanics. But what the machine learning model is able to do is disentangle that total interaction energy into components, and that those components can be very physically intuitive. So for example, we can disentangle that total interaction energy into an interaction of pairs of atoms, triplets of atoms, 4 atoms. What does the configuration of 4 atoms together bring to that interaction energy? And this is a very old idea that has not, before the machine learning methods came around, wasn't really possible to carry that through beyond 3 particles, just because the mathematics wasn't there. But now we have the machine learning models with which one can carry this out to arbitrary number of interactions and with great accuracy. And that actually gives us new understanding of the physical theories which we are modeling.
So just before I move on to the final question, given that one of you is from academia and one of you is from industry, just what are your thoughts about how industry and academia have been working together?
Yeah, absolutely. So I think, I mean, I was speaking about this with Gabor earlier, but I think it's unusual in that actually a lot of the fundamental research, I think, actually comes from academia in this domain, which you can kind of contrast to other areas like natural language processing, computer vision, where you have these kind of tech giants like the Google Brains, the Deep Minds, the Microsoft research, Facebook research, where actually a lot of these are kind of major innovative hubs. I think in machine learning for molecules and materials, actually, a lot of this actually comes from academia and increasingly startups. And what you're seeing now is there's actually some of the ways that these big pharmaceutical companies, for instance, are actually kind of gaining this insight and knowledge is to actually work very, very closely with startups. So it's a kind of a little bit of a different model to these other domains. But yeah, in terms of collaboration with academia, maybe you could even speak a bit more about that, Gabor.
But I think pharma, the area that where your company is very active, is an example where there is a close collaboration, and that where these methods have really direct impact into what industry does. In other areas, in materials modeling, I think the pipeline to exploitation is much longer. So if I make a better model for a material using our machine learning techniques, then that will be picked up by another academic group that doesn't develop these models, but uses them to understand something about a model material, pure carbon, for example. And then there'll be an industry, a company which uses that new understanding to tweak something about their process in how they use carbon coatings, for example. But so there are 3 steps away from the machine learning model that I have created until you reach sort of an industrial interest. And that's more generally true in materials modeling.
So I'll just move on to my final question, where you can put your predictive skills to the test and see, where do you think we will be 10 years from now?
So I think, as I mentioned before, I think this side of generative modeling is going to just become extremely important, because this kind of allows you to actually get past doing a lot of these kind of even sort of simulations with long time steps, and actually try and just directly generate or predict, generate the kind of candidate material that you're really interested in. I think another area that's going to become extremely important over the next 10 years is actually using quantum computers to derive these kind of quantities. So as actually, I think Feynman, who, he was sort of coming up with the foundational principles of how a quantum computer could work, said, actually, even at this stage, he said, this is going to be really good for actually modeling physical systems, because it relies on the same kind of quantum mechanics that actually these physical systems rely on. And I think that we're in a super exciting time at the moment where we're seeing this kind of Google quantum advantage result. This is on it's interesting academically, but they're not solving a useful problem. I think the next kind of step for quantum computing that's going to be a landmark step is actually this kind of practical advantage, where we actually can do something of practical utility on the quantum computer that just couldn't really be done in any other ways. And I think, as I was describing before, we have these sort of different levels of theory where progressively you include more of the quantum mechanics, and actually some types of systems, and very, very interesting systems, things like superconductors, superfluids, and other materials, and even in a pharmaceutical setting, these quantum effects dominate. And so actually, even if you're using a very expensive method on a classical machine, actually you're going to get completely inaccurate results. So there are a bunch of methods that actually we know will work for this, but they're so computationally expensive that we can't do it for more than just say 15 atoms. It just breaks. And what a quantum computer will allow us to do, this is to do with the exponential scaling of the wave function, will actually allow us to break through that and actually start to accurately model these kind of systems that were literally just previously out of reach. So these are things that were just kind of more or less impossible to model accurately. And so quantum computers will help there. Something that I think is important to know as well is that these things, using these methods on a quantum computer, will also be slow, so that you won't be able to do high throughput screening with it. This will still be difficult. But I think where the real kind of magic will happen is actually combining the output of these quantum algorithms, these quantities derived from these quantum algorithms, with the machine learning to actually make this faster. So the machine learning will understand when it needs a quantity derived from a quantum computer. So I think in this regime, you're going to get this kind of very, very high level of accuracy to do with these quantum characteristics, but also the speed from the machine learning. And I think that's going to be, in the next 10 years, I think we're going to start to see this happening, and that's extremely exciting.
So there's a very definite role for quantum computing you see in this area.
Oh, absolutely.
Okay.
Yeah.
That will be very exciting. I think what will definitely happen is that these machine learning methods will make their way into the current simulation software that we all use in academia and in industry. So that's just starting to happen. I think it will be completely standard that these computational material simulation software will have machine learning built in to make it faster.
Okay. So I think that's about time. So thank you very much for the discussion, and we'll now move on to some questions. Firstly, in the audience. Oh, there's lots of questions. That's good. So if you start just there, and yeah.
thank you for the presentation. Do you think, just from experience, that having something as powerful as machine learning or the machine learning methods could affect the scientist's ability to ask the right questions?
So the implication of your phrase is could it affect negatively? I think it's the other way around, actually. So I think that these methods allow us to ask questions which we couldn't ask before. Let me give you an example. When we do a long simulation of a dynamical simulation of what will happen to a piece of material, we put in some approximate model, and then we get out at the end of the simulation some property. And we don't really know, and we weren't able to ask before, how does the inaccuracy of my model that I put in affect the prediction? Because that simulation is too complicated. And before, the models that we put in weren't systematically created. We didn't know, we couldn't have good control over the errors of that model. But machine learning models, which we can also plug into long simulations, have controllable errors. Even mathematically, one could take those errors and propagate them through the simulation and start asking this question that has never been asked before in computational modeling. What is the error bar on my predicted property due to the lack of convergence of the model that I use? And that's an amazing question. And it's sort of obvious when you think about when you pose it, but it's never been asked before because we didn't have the fast ML models with which to ask this question.
So just with, yeah.
Hi, yes, I'm interested. Was it active learning you were talking about? Is that what it's called?
Yes, active learning, yep.
So can I just check if I've understood this right? Basically, the system asks for the physical data that it thinks will be useful.
Exactly. So, and this comes back to what Gabor was just mentioning. So you can do this actually based on uncertainties. So if your model it tries to make a prediction at a high level, and it has very high uncertainty there, then what you might say is, rather than just letting it make that prediction, actually let's grab that data point, do the expensive calculation, and feed it back to the model. But if the it has low uncertainty, we say, well, actually, probably actually giving it this data point is actually not going to help very much. So based on these uncertainties, you can actually make a very intelligent, the model can make an informed choice about where and how it collects the right data to reduce the overall error.
Okay, I was just sort of taking this forward. I mean, would it get to the point where the system is actually saying, do this experiment and get me the data?
Absolutely. In fact, yeah, this is something at Rahko that we work on, exactly like the machine learning dictating where and what kind of experiments do we need. Because actually, as there's a hierarchy in these kind of simulation methods, it's a hierarchy of the experiments that go from kind of cheap to expensive. I guess one of the most expensive ones is actually putting it in a human. And that's the one you really want to make sure you get right. So, yeah.
So you think twice before it says, could you just pop this in somebody's mouth and see what happens?
Well, exactly. And I think that, yeah, exactly. And I think actually what you'd hope to do with these kind of methods as well is actually to make sure that by the time that you are testing this drug on a human, that it's really as safe as possible. And I think that actually this is another kind of enormous piece of potential of this kind of machine learning and generative modeling is to make sure that you're really only taking forward the very, very best candidates that you can, the safest candidates as well.
There's a name for this question. It's called experimental design. And that's a field in which you use the machine learning model to tell you which experiment to do next. It's particularly worth it if the experiments are very expensive or some very costly, perhaps in risk.
Do you think it might put scientists kind of out of the loop eventually?
These are actually, when you look at them, mathematically, they're rather simple mathematical formulation. So this, if I have a function here and it's like this, but you don't know, you ask me where I should tell you what the function is. That's the way this is. But the scientist's job isn't really replaced by this. The scientist's job is to say which function to model, or why should we do this, or should we do it in a completely different way, right? So those are higher level questions, and we don't waste the scientist's time because of the drudgery of asking where do I take my samples exactly. So I think these are tools, and they allow us to be better scientists.
But maybe it changes the skills the scientists need if they've got to use these kind of things.
Oh, definitely.
Yeah.
And we try to teach these techniques and these tools as early as possible. I think that's very similar to statistics. So if you think 100 years ago, you could have done science based on examples and anecdotes, and when I did this last week, that's what happened. So maybe I should do this next week. And statistics puts that on a more formal footing. And now you wouldn't dream of doing science without some understanding of statistics. And that's and machine learning in some ways is computational statistics.
I think though that so for instance, if looking at fields like kind of computer vision or natural language processing, I think it's possible for someone without just say any knowledge about medical imaging to actually create a model based on a data set that ends up being, probably having similar performance to an expert in diagnosing a particular disease from a medical image. But I think actually in machine learning for molecules and materials, actually you really need to bring you really need to understand the physics and quantum mechanics to be able to construct models that are going to perform well. So I think in this way, I could say it's sort of a harder domain, because in order to solve problems here, you really need to bring people from the best of machine learning and people from the best of this kind of computational chemistry together to really actually make good progress. And I think that's also why it's particularly exciting, but I think it does make it more difficult.
I think, question just there.
Yeah, so a rather open-ended question. Do you think E equals BQP?
No, I hope not. No, I don't. Yeah, I don't think so. So I think, it's not been proved, but yeah, my bet would be on no.
So you had a question? Yep.
So given the cost and time involved and budget constraints in building and executing models, is there any current data collaboration or data sharing amongst the community across industry and academia, or is there just too much at risk financially? So now in the biotech, computational biology realm, they've started to make some open databases. I wondered if there's anything similar.
Yeah, so people are starting to look at this, but I think this is a massive bottleneck. So some of the best data sets are actually kept and protected in-house. I'm talking from a kind of pharmaceutical perspective, but they're kind of kept and guarded very, very secretly. And I think, but actually, if we combine all these data sets together, actually the sum of the parts would be more powerful. And I think that's why there's people now starting to look into things like kind of federated learning, where each party can't necessarily see the data or can't actually understand what the data is, but they can derive benefit from a machine learning model trained on the much larger sum of data. So yeah, certainly I think that's going to be something over the next 10 years that's going to change as well.
There's sort of two schools of thought on this. One is that the more data, the better, and everybody should publish all their training data, because that's the only way to go forward. But actually, if you think back to the discussion on active learning, that suggests that other people's data isn't actually that important, because I'm going to have to make my own data anyway. My own machine learning model will tell me where to take the next piece of data, and that depends on the model itself. So somebody else's data actually isn't that useful. And we find this all the time when we make models of quantum mechanics, and there are some people love to compete. So they publish a data set, and who can do the best model based on that. And I look at the data and say, I really want to do better, but I wish you just give me that one other piece of data, because my understanding or my model says that's the most important, and it's not in your data set. So it's not clear how useful that is.
I think there was one last question, and then we're going to have to stop. So yes.
Thanks for a quick talk. You mentioned ML as a tool. You're building better simulators that scientists can use, but you also mentioned as accuracy. We're not happy with 99. Maybe we want 100. We want alignment. At what point, if you have a model that works perfectly, can you maybe prune this model and actually find new science? Like, is there an opportunity to use ML to discover science rather than just as a tool for simulation?
So when I say 99 is not enough, it's very interesting. The answer isn't 100, right? Because of all the constraints of data and dimensionalities, it's not that we make a perfect model. I want models that are 99% accurate most of the time, and never worse than some other threshold. So global guarantees of non-craziness is actually the prized thing. Regarding your other question, I think that there is scope for getting understanding. So the example I had earlier about the interactions of 1, 2, 3, 4 particles, and that's a machine learning result. Another example is what I talked about earlier about generative modeling, where if you are able to find a latent space in which you move around and each one of those points in this hidden space corresponds to a molecule, and you can understand that which molecules cause greater or less toxicity, or which molecules bind to a certain protein, then looking at that latent space and what features of the molecules leads to what properties. This is also a bit reminiscent to the previous topic of error propagation of models to properties. I think those are real new questions that we haven't been able to ask before, and machine learning can open those up and give us new understanding.
Great. So I think that's all we have time for, but thank you again for your input.
Thanks,
Thank you.
Alice.
Thanks a lot.
Thanks, everyone.
Thank you. What a great session and awesome questions. I think this is my favorite crowd. So next up, we have lunch. I know everyone's super excited. There's going to be food at Leiterman. So it's just, you come out the building and it's on the other side. But the amazing Cognition X team will show you how to get there if you do get lost. And then at 2 o'clock, we'll be talking about drones, the telecom market, and sustainability. So lots and lots of exciting things coming up as well. But you can also find out more about that on the app and speaking to the team and also networking with each other. So once again, another round of applause for our amazing moderators and speakers, and see you at 2 o'clock.